Yes, lovely. So I just thought I'd put the poster up just because Paul said that it counted towards presentation marks. So I just thought I'd quickly flash that up if you'd like to have a read of, sort of give you a quick summary of what my project's about. So it's a 4 to 20 milliamp process simulator. I'll just quickly go through it. So the target audience for this project was for PLC programmers, so programmable logic control programmers. So that mainly revolves around the water industry. Water purification plants and stuff. That's where my father, he works in PLC programming. So that's sort of the area that he works in. So quite a lot of the examples and the scenarios that I'll be giving you today are more lean towards valves than maybe other PLC sort of areas. I'm just going to load up the PowerPoint. This may take a couple of seconds. Lovely. So these are the project milestones. I don't know if you want me to go through them or let you just quickly have a read of them.
I think I just wanted to ask at the start, Zacc,
yep.
How long is your presentation?
All in total, I would say the presentation with all the videos is way too long for this presentation, I'd say. I've got 5 modes and I've tried to put enough information into all the modes. So they're probably around about 4 minutes each. So what I was going to do is just quickly run through a couple of the project management things inside this PowerPoint, then maybe get you or Toby to pick a mode. I've got a quick video on the mode, that's 4 to 5 minutes. And then after that, just go.
Don't worry about the project management, concentrate on the stuff.
Okay, so we'll skip the project management and we'll go straight to the project design then. And that should cut it down to around about 20 minutes.
Have you got it? I couldn't quite see a slide. I mean, I had a quick look through your slides.
Yes.
I couldn't quite see the slide about the project aims and objectives, and the rationale behind it all. You know, why are we doing this and so on? Is there any, I think that's a good starting point, really.
Yes. Yeah. So that's why I tried to put the poster in at the start, just to give you a little bit more of a background on the poster.
So if you imagine that I know nothing about it.
Okay.
If you imagine I'm a difficult customer.
Okay.
And I know nothing about it. Just convince me that this is worthwhile doing. And
okay. Yeah. So basically, this 4 to 20 milliamp process simulator, it's used in the PLC industry. So when programmers of PLCs need to change code for any sort of reason, when they're working in the industry such as the water industry, you can't turn off a water purification plant. Just turn it off, because then no one will be able to wash their hands or anything. The 4 to 20 milliamp process simulator allows the user, the engineer, to plug, it plugs this system in between the let's say the float switch or some sort of instrumentation and the PLC, and it will basically simulate a pump valve, it will simulate a butterfly valve, it will simulate a curve. So it's basically a simulation tool that the programmer uses to that the programmer can use to show to the end client that this is working without having to turn the whole plant down and turn the whole plant off. So future designs of this was to be able to actually record the a whole diurnal 24-hour pattern to allow more use, but I've quickly turned this into a simulator instead of a recorder, this first section, and then maybe later on development turning it into a recorder. So it's a simulation tool for the engineer, because it's very hard to simulate actual real life responses in the industry because they can't turn things off and simulate using the correct, using the actual data.
Right. Was it your own idea originally, or was it somebody that gave this to you? Or
it was a little bit of both. I worked for my father between the first and second year, and he's a PLC coder, and also he works for Peak 42. They've just been bought out. I can't remember, Rogerson's Bridges or something like that now they're called. And I was speaking to Dave Forshaw, one of the bosses there, and he said, well, we need this. And Dad was saying, well, I can't do it. I can't just turn off the plant for you to show you this new program that I've done. We're going to have to either just go for it or not, because we can, I think it would work properly. However, I can't just plug in, I can't turn the plant off to get the actual data in to show you it working without actually programming the actual PLC. So it's more of a simulation tool that they could go, yes, well, quickly, if we clip this in, simulate what response we would get out of this, this instrument, this is what you would get. It would just allow ease of use. So yeah, I've got Peak 42 were one of the sponsors that gave me some of the kit.
But it simulates a physical piece of hardware almost, doesn't it?
Yes, yes. It will simulate the response of a float meter or a laser rangefinder, something like that. So all of these instrumentation use 4 to 20 milliamps because they're normally across, say, the actual PLC, the central hub is a good couple of miles away from the actual instrumentation. So they use milliamps instead of volts, so you always get a good signal coming through. Obviously, because if we use volts, then the signal that will be coming through will be millivolts at the end of it, where with amps, it will always stay between 4 to 20 milliamps. So just going into the actual design of the project. So the input circuit, this is what I've got at the moment. So the 4 to 20 milliamp signal is coming through the top, and we're just measuring over a shunt resistor. That then creates the different values. So at 4 milliamps over the shunt resistor, it'll be roughly 600 millivolts. And then that voltage goes into an ADC, 12-bit ADC. And then I'm sending that 12-bit ADC to the MCU, where the MCU is buffering that, putting it into an average buffer, which I'll go over in a bit. So before all this time, there were some more. I was going to enhance the input circuit a little bit by using more protection, because obviously, with these being 24-volt systems, there could be spikes in anything. It's normally a high voltage area, so I wanted to put a gas discharge tube in, a varistor optocoupler, and some input fuses just to prevent any large protection spikes or anything like that, any large spikes from occurring, damaging the systems. And then that's just the optocoupler. That's how I changed from the shunt resistor to measuring across the optocoupler. So the optocoupler completely isolates the inputs to the system to the MCU. So there's a complete isolation there, so there won't be any damage occurring from if there was any spikes in voltage or anything like that. It wouldn't damage the MCU. Now going to the MCU design. So like I just said, then after the ADC, it goes to the MCU. Key features about this MCU is that it's a multi-threaded system. I'll go on to, I'm utilizing a TFT capacitive touch LCD, fully touchscreen. And what I really want to put across is that with this LCD, I've managed to use indirect addressing, which saves a lot of memory and allows ease of expansion. So I'll just go over those. So looking at the input buffer, so the start is where the voltage would be coming in, and every 0.1 second, sorry, with loading the ADC 12-bit value into a FIFO buffer class, and then every 0.5 seconds, we're then averaging that sample. So we're always trying to get a consistent average. Now PLCs, they don't require a quick change in signal. So this doesn't have to be, it can be quite a slow process, thus every 0.5 seconds. It doesn't need to be every 10 milliseconds, because the changes with these switches only, they're sort of very, very slow. So that's the input. Then this is the actual program flow for the system. So the splash screen is the main screen. I'll show you that in a second. When you click main menu on the main screen, we go to the we go to the main menu page. So from the main menu page, you select the mode that you would like to use, and then you go down into the set point pages. Now, just around about here, I'm so let's say we click tracking, for example. I'll go through tracking with you in a bit. It only requires 2 set points, the input ratio and the output ratio. So we don't need set point page 1. I've implemented in my code that it reads that you don't need more than 1 set point page. So it will jump straight to the set point page 2, which is the page, as you'll see in a couple of minutes, that's got the run page on it. So that's saving time for the user and minimizing the amount of pages that I have to create. Where if I had to do this for each page, for each mode, sorry, I think just this one process would take up 10 pages worth of memory instead of just 2 pages worth of memory in the system. So that's sort of the main sort of focus of this project, is sort of going indirect addressing route. So showing this system can be easily expanded. So the advantages of indirect addressing is that it allows the mode to have independent set points. It's ease of use, ease of access, because it uses pointers, and that it's very, very easy to expand. So if the customer came back saying that I need a new mode, I could quickly program that mode in probably half the time that you would be able to normally, because normally you would have to make the new page, where I've already got that page made, and it will just load the information into that page. I'll be able to show you that in a couple of minutes. And then this is just the output flow diagram. So when I click run on the LCD, it loads the calculations into the output variable. And then it scales the output variable, so to make sure that it's in between 4 to 20 milliamps output, and then it outputs it to a 12-bit DAC. And then I'll skip this one. So this is this LCD screen that I'm actually using. So the original design of this project was to have the LCD screen as a screen, not a touch screen, just a straight screen, and use external switches. However, I decided later on that I wanted to utilize the full capacity of the screen, so I turned it into a touch screen, getting rid of the external switches, which also later on in the design meant that I could try and turn the system into a dust-proof container later on. So I've got a quick video of how the actual screen works. Can you hear the volume here?
Very tiny.
Very tiny. I'll turn this up for you. Turn this up for you. Can you hear this anymore?
Just a bit better, but not entirely.
I'll just pause that there because it just shows off a couple more. I'm conscious about the time. So basically what I'm trying to show in this video is all about the indirect addressing. So instead of having safety information pages, one page that prints each and every time, I'm basically printing a shell for the page, and then through the use of case statements and indirect addressing, it's then populating that with the data that we called for. In this project at the moment, there are 5 modes. Probably I'm conscious about the time, so would you like to pick a mode from 1, 2, 3, 4, or 5? It's probably the easiest. There's a short video at the end that will take roughly 4 minutes of each of them. So did you want to pick a mode to go through?
Well, which one is the most informative then?
I would say probably the pump curve simulation mode. So the first 2 modes, the process meter mode 1 is basically acts like a DMM. The process meter with engineering values is the exact same as mode 1. However, it uses engineering values, which is what the actual industry uses. It uses a value from 100 to 0 instead of 4 to 20 milliamps, so 100 being 20 and 20 milliamps, sorry, and 0 being 4 milliamps. Tracking with ratios is it follows the input signal via a ratio. Pump simulation, it's basically the user puts a pumping curve, which is normally found from the manufacturer's data sheets, into the system, and then the system will print that out on the screen. So if the programmer would like the pumping a curve simulation to come in, like I was saying earlier, the output of the pump to come in at, say, at 50% flow, they would like to see the output. This outputs that pump that they've got at 50% flow. And then a valve simulator simulates a valve, turning on and off.
I was going to say let's try mode 4 then in that case.
Mode 4?
Yeah.
Pumps in mode. So this mode simulates the characteristics of the output. So mostly the pump curve follows an exponential curve. So these are always derived from the data sheet. So this system basically, we've got 2 set point pages, allowing the user to put 5 set points in each page. So there's 10 set points altogether. So what we do is we ask the user to put every 10% increasing in the amount of flow. They put the corresponding pump curve value in there, and then later on it'll, when you click run, that percentage that you want through, it will work out the pump curve from that. So I've got some pseudocode on how this C code worked. And then also I've got the actual code that I used in the system.
I was going to say, when you run the video, I'd suggest you talk over it.
Yeah, sure.
I'd pump my volume up to hear the other one.
Yeah. Oh, sorry. Yeah, sorry. Yeah, I'll probably copy what it says in the thing. So these are the four screens. So the top left screen is the information page. So this is when you click the info button next to the mode. So it just gives a brief description of what this mode does. So this mode reads the input of the system and compares it to the lookup table and outputs the result. So as you can see in the pump simulation set points page, the page below it and to the top right, these are where you put your extrapolated data into. And then when you click run, it will it'll go to the run screen, which is the green screen below. And then from that screen, it will output the milliamps out compared to the input to the system. It's very complex to speak about. If I just show you the video and see if I can crank this up.
I talk over it.
Okay. So basically, this is the pump simulation page. I'm just going from the main page, and then I'm clicking the information page in this video. So like I just said, I just showed you an information page. I'm just reading out at the moment what it says on the screen. So to give a little bit more context, all pumps are supplied with the manufacturer's data sheet, and basically what we're asking the user to input is the pump curve at that particular head. Do you understand head? So the amount of water that it's forcing at that rate. So we're asking the user to put the data sheet's extrapolated values into the set point pages, and then from that in between 0 and 10%, 10 to 20, to 20 to 30, put that extrapolated data into the set points, and then it'll when you click run, dependent on the input flow, it will output the representative flow from the output. So I've in this example, I've already pre-filled it with a pump's characteristic flow. So on the bottom screen, I also created a test bench on PLC using ladder code. So I'm just setting it up at the moment. So I'm just going back to the system. So when I click run, the output should be 0 for quite a long time until it reaches roughly 40, in between 40 to 50%. So that's roughly 10 milliamps, and then you should see the curve slowly, the red line slowly print out the pump characteristic curve. So at the moment, I've in the simulation below, I've utilized a sawtooth simulation that I created. So that increments the milliamps in the system by 0.25 milliamps every second. So you should see the pink line going up in every 0.25 milliamps every second. So you can see the pink line climbs until roughly 10 to 12 milliamps, where then the red line will start to print out the characteristics of the curve. Obviously, like I said, the normal curve is exponential, so it only changes a little bit at the moment. As you can see from the top, the output from the process meter is just starting to move from 4 milliamps then to 5 milliamps now. So the closer we get to 20 milliamps, it then outputs the process meter curve, so the pump curve. So it will slowly, as it increases, it'll then, the red line should print out the inputted exponential curve that you've placed in. So you can slowly see the red line is now outputting the characteristics that we placed inside of those set points. So at 19.5 milliamps, it was asking 19.5 milliamps into the system. We said that it needed to limit it to 18.3 milliamps out. So as you put the input into the system, it then outputs the characteristic curve. So that's the pump simulation run mode one. And then it just goes straight to the valve simulation mode. So I'll just skip over that. And then that's the end of the that's my final piece. So it's a little bit messy. The big box on the right is the PLC that I managed to acquire from Peak 42, and I'm always using actual data from the PLC to measure the system. So I've tried to make it so the PLC. So I'm using actual data from the PLC. So there's no difference between the small PLC and a big PLC. They're all outputting the same sort of data with the same. They all use the same output cards. So I'm trying to make it as real life simulation as possible. So yeah, that's
so the hardware we're looking at actually works, Zacc?
Yes, the hardware that we're looking at actually works. So I've created, if I click back, go to here, I've created, this is my PLC test bench. So this is, right. I created this test bench using ladder code, ladder coding on the PLC. I'm conscious about the time, but this is what I used for test benching everything. So if I quickly just go on to process meter mode and output 10 milliamps. Sorry, I'm just using the touch screen at the moment. You can see that at the moment I can input to the system any sort of value that I'd like to. If I wanted to input to the system 8.2 milliamps, you can see the pink line actually shows the input. So if I set this output to 10 milliamps, for example, if we click run, I'm just clicking run now, the output should, there you go, it's just jumped to 10 milliamps back into the system. So it, my system works with the hardware of the PLC.
Right.
Made sure that it works with the input cards, the most up-to-date input card that there is. So yeah, I can change the output to, just because I'm using the process meter mode, I can change the output to the output from the process meter to any value between 4 to 20 milliamps. So if we wanted 10.5 milliamps.
So you've obviously got a working system. So yes. How does this differ from what you were hoping to achieve with COVID? Because it looks, there's not. It seems that everything's there, but what?
Sorry, the meeting is just about to run out, so it may kick us out. So basically, what differs from this one to the before COVID. So I'm just going to call this the COVID edition, 4 to 20 milliamp process meter. So this one is more of a simulator, where my original idea was an actual recorder and simulator. So the simulator bit, this was more the 70% to further improvements of the project. Unfortunately, the SD card that I was, the SD card and the SD card reader that I was going to use became out of stock straight away, just as COVID started. So then the recorder part of this project sort of became a lot harder to get hold of. So I decided to get rid of the recorder part and turn it into a simulator instead of a recorder. But inside the project, I can still use the memory inside the project to record. However, I can't use an external SD card to then, for example, to get to record the information, then plug it into a computer and see all the information on an Excel spreadsheet. That was my original idea. So I've sort of shifted it down from a recorder and simulator to just a simulator.
Right. And what did you find to be most challenging in this project?
Definitely the touch screen. So I've got I'm going to try this quickly. If I go to videos, tell me if this works. I've got a touch. Can you see the touch screen? It's very, very bad focus. Sorry, I've got not a very good webcam. So I've got this.
Yeah. I just see it, yeah.
There we go. We should see a little bit better now. So I've got a fully integrated touchscreen. It's very, very hard to see. That doesn't really help at the moment. So yeah, getting the touchscreen working was really, really hard. Obviously, I've never done anything like touchscreen before, so this was completely new sort of adventure.
Right.
I feel like I've really done well, obviously, because my original design of this LCD, for each of these buttons here, so we've got 5 buttons for each mode. There's five information tabs. My original program called a page for each of those designs. So that's already just on page 1, 10 pages in the memory. And that's why I changed it very quickly to indirect addressing. So instead of needing 10 pages now, I've actually just got 1 page that does the actual, if you look here, if I click information, it calls the information page. So it prints out the shell of the page and then it populates it with information. So definitely the touch screen and the getting everything to work inside the screen, trying to make it a good user interface or machine to user interface. So definitely the most challenging part.
Okay. Thank you.
I had to change libraries for that too. There wasn't any direct libraries that let me print out running values. They were always static values, so I had to go into libraries and readjust the libraries that were provided.
So your project involves both hardware and software, essentially.
Yes, it definitely involves hardware, software, and then PLC software and hardware too. So 2 different languages.
Yes, it's across the board, yeah.
Yeah.
All right. Okay, thank you. I think I've no more questions to ask.
Any more from you, Toby?
No, I think that's it for me. I think very good. As I say, it's a shame you didn't get it boxed up in your neat box.
Yeah, I'm sorry. That boxing idea was. I think I didn't show Emmanuel the renders that I did. So this was the render that I did on Google SketchUp. So I could have printed it all out, but due to the fact that I didn't have enough time to make a PCB or anything like that, I would have just shown you a 3D printed piece of plastic with nothing inside of it. So I decided against printing all this. But these were all the different components. This red shell here at the bottom was a conductive polymer. I researched you could utilize conductive polymers, and that would basically act like a Faraday cage to stop any signals from the outside world affecting it. So essentially making it almost EMC compliant with just plastic. So yeah, it's a shame that I couldn't get that already.
Okay, all right, thank